recording. So I've got us mapped out to do 5.4 and 5.5 next week. But what I'm tempted to do instead is to bring kind of like a worksheet for trig, and we kind of work on the worksheet so we can kind of just solidify what we have because it's the last week of classes. And so I think that's the way I'm leaning. So we'll do 5.2 and 5.3 today, and then and finish our pizza delivery problem. And then we'll do kind of, I guess in a way, trig review on Tuesday, and then final exam. Kind of an overview, but any questions that you have, you can bring them in. Yeah. And then that's it. And then final exam time. Any questions about that before we start here? Does that sound? I know everyone's like, I don't know, you're the boss. Just create work. All right. So I think that will be best for us. And we had this problem. So last week, nope, Tuesday, feels like a long time ago. We did my favorite problem, the ant problem. This is going to be a similar problem, right? Where we have a circle and we have a line that goes through the circle and we need to find the intersections, all that fun stuff. And so here we go. I said, try on your own and use this for a review on Thursday. Well, here we are on Thursday, so I'll delete that. And I did put the answer here, which I'll bump down by request, just so you could try it. I did go ahead and already put my axes, and so it's going to be a little bit shifted because I guess I did a weird grid. And so it's going to be 1, 2, 3, 4 in for the y-axis, and 1, 2, 3, 4, 5 up for the x-axis. In a town, Main Street runs east to west, which means we need our coordinates here. Never eat shredded wheat, which means that this would be our main street if it runs east to west, and Meridian Road runs north to south, making this, Meridian. A pizza store is located on Main 2 miles east of the intersection of Main and Meridian. The intersection is here, and if we use these ticks as miles, I guess, then 2 miles east puts our pizza place here. Felix loves trig.
So small.
Yeah, but he just leaves whenever he wants. Oh, I love that he started showing up here. He didn't used to be around. And then one day, he just showed up and hasn't left. There was some confusion. Someone brought him home thinking he didn't have a home, but then someone's like, that's my cousin's cat, so he does have a home. He just likes to be here. All right. So if the store advertises that it delivers within a 4-mile radius, how much of Meridian do they deliver to? And so we need to map out the delivery radius, 1, 2, 3, 4, and down 4, 1, 2, 3, 4. Let's see if I can pull this off. 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. Draw a circle connecting these. Ish. Ish, ish, ish. Close enough, I guess. Doesn't want to extend. Anyways. Call that our delivery radius, right? So here, R is 4. How much of meridian do they deliver to? So this here is meridian, right? And so we want to know, well, how long is this stretch? Which is very, very similar to the ant problem. Right? I'll do a highlight here. Maybe an orangey glad. So this is what we want to solve, right? That stretch. To find that length, right, might be nice to know what these 2 points are, right? And so we need the points of intersection. So we need the points of intersection. But to get the points of intersection, what do I need? I need the equation of the circle and the line, right? So I can set them equal to each other and solve for x and then solve for y or vice versa. And so here, that means we need the equations of the circle and line. It is a line, but it's a really nice line, right? This line is the y-axis, which is at x equals 0, right? And so here, we can tackle that right away. Oops. Looks like 6 there, 0. So that's what's nice about this problem, as opposed to the ant problem is a little bit higher level, right? Because we have a line with a slope and we have to find what the equation is. And so it incorporates more information, but how you solve them is the same. So I still need the equation of the circle. And so the equation of the circle is going to be x minus h squared plus y minus k squared is equal to r squared. And that's from last day, and maybe I'll go snag it from last day. Just so it's on your formula sheet too. But I feel like I thought this would be closer. Copy. Wait. Make a mini version there. We already wrote it out. X minus h squared plus y minus k squared plus r squared. Now, this is for a circle centered at hk. Now, for us, where's our center of our circle? Our center of our circle is at x is 2 and y is 0. Which means my h is 2 and my k is 0. So a way nicer equation than what we were working with last day. We also know the radius. The radius is 4, right? They're 4-mile delivery radius. So if we sub those in, we get x minus 2 squared plus y minus 0 squared, which of course you don't have to write. Yes. Oh, you got it. I'm out of here. I'm out of here. Oh, there you go. You just have to talk opposite to cats. So then we have x minus 2 squared plus y squared is equal to, whoa, I did something weird here. 4 squared, not 4 to the 6. I think I was jumping the gun to 16 somehow. Not sure. I'm going to leave the equation of the circle like that, right? You can expand it if you want to, but all we're going to be doing, right, is, okay, so now I have an equation of the circle, right? And to determine if I should expand it or not, then what's my next thing that I want to do? I want to find the points of intersection. Well, I know the points of intersection are at x equals 0, right? And so I know for both of these points, right, it's at 0 something and 0 something, oops, something. Leave it open. And so to find the intersections, substitute x equals 0 into the equation of the circle. So I get 0 minus 2 squared plus y squared is 16, which means I get 4 plus y squared is 16. Which means that if I subtract 4 from both sides, I get to 12. And then if I take the square root, try to keep it on the same page here, I get the square root of plus minus root 12. Oh. Oops. Bump this around here. Root 12. Let's see here. The root of 12, whoops, is roughly 3.464. And so the distance, maybe I should keep. The distance, this circle is centered just off of the y-axis, but it's still on the x-axis, right? So for that reason, it makes sense that each of these distances are root 12, right? And so I have to go down root 12. Oops, let's see here. The root of 12. So here, I have to go up root 12 and down root 12, right, which is the negative version. Negative 12. I guess I don't want to have the negative there because it's still a distance, but in the negative direction. Okay. So I do want the negative here, but not here necessarily. You can put it on there if you want. Okay. Which means that the distance is going to be 2 times the root of 12 or root 12 plus root 12, however you want to do it. Totally fine. All right. And so therefore, the distance is 2 root 12 or hopefully it's 6.928 miles. Otherwise, what I stole is no good. Oof. 28 miles. And we didn't have it. Nice. This one, a little bit gentler, but same idea, same concepts as the ant problem. But that's why I like the ant problem. It's elaborate, fancy. Any questions about this one? No. Ah. Then on to the next one. Section 5.2 is on angles. Yeah. For wet, we're going to focus on degrees. I suspect you'll be working mostly in degrees for work if you're doing any angle measurements, right? You might be familiar with radians. I'll introduce radians, maybe. Yeah. No, radians. But we'll work with degrees, just because in the field you would be working with degrees. Radians have some benefits, right? They're unitless, which is nice, right? Especially if you're gonna working with your units. Ugh. But in general, right, angles have the same properties, so it doesn't really matter. You'll want to make sure that your calculator is in degree mode, right? Because we'll be working in degree, and you'll be able to tell on mine, there's a little D highlighted, and there's a subtle DRG, and so it'll tell you what mode you're in there. On my TI-83 in high school, you know how they make you buy the TI-83? They still do that. Anyways, they used to make you buy these huge calculators and then get to university and you're not allowed to use them anymore. So weird, but I used to have a sticker, radian or degree mode, but we'll just be in degrees. So what's an angle? You might say, you might know. The measure of an angle is a measurement between two intersecting lines or line segments or rays, depending on what you want to call them. And so just for some terminology here, this is your initial side, right? And then ending at the terminal side here. Then this measurement here is the angle. And so, of course, it's a rotational measure and not a linear measure. But for degrees, a degree is a measurement of angle. And so one full rotation around a circle, you might be familiar, is 360 degrees, which means that 1 degree is 1/360th of a circle. Right? And we've got some common cutoff points of our circle, right? 90 degrees, 180 degrees, right? That kind of thing. And so one thing I will highlight, an angle measured in degrees, I guess I'll highlight the whole thing. You have to include the unit, right? And so that's where the benefit of radians comes in, because they're unitless, right? And so, because units can make things a little bit messy sometimes, as I'm sure you've found in other courses maybe. So you can say degrees, or you can use this little degree circle, which you're probably familiar with, right? And so 90 degrees is 90 degrees. And 90 degrees, we indicate by our initial side, our terminal side, and a little square in the corner indicates 90 degrees. And that's true for triangles too. Standard position. So when measuring angles on a circle, unless otherwise directed, we measure angles in standard position, which means that we start at the positive horizontal axis. And so this is our positive horizontal axis. And so this is your initial side, right? The positive horizontal axis. And then counterclockwise rotation, right? And you can go around once, or you can go around 1, 2 times, and you can end up in the same spot, right? So, which leads us to coterminal angles. Once you've gone around once, boom, or maybe here, dink, you can go around another time, right? And you end up in the same spot, which is what a coterminal angle is. And so after completing their full rotation based on the given angle, two angles are coterminal if they terminate in the same position. And so here, this is the terminal side. So if they end in the same spot, then they are coterminal angles. And they would have similar properties. We usually, I'll make a note here, we usually denote angles with Greek letters, such as theta, alpha, gamma. Those. How familiar with Greek letters are you guys? From your other courses, do you use theta is a good one, right? Phi, maybe. So we usually denote angles with Greek letters. Theta, phi, alpha. Oops. Those are kind of the common angle Greek letters. There are more, but fine. Gamma. Go on. All right. Mu. Mu. But we don't tend to use mu for angles because mu is for the population average. Okay, that's not for us. That's for when you take your stats course, which you will. So find an angle theta between 0 degrees and 360 degrees, right? And so even if we've looped around a couple of times, we want to stay in the 0 to 360 angles. Coterminal with the following angles. And let's see here. I'm gonna add a page, I think. Wait. .400 degrees is more than 360, which means I've gone around once. And so if I kind of map it out, it means that I start here at my initial side, and I know that I've gone around definitely one turn, right? And then we want to figure out how much more past that one turn. And so I'm going to do 400 minus 360. which is 40, but let me just be confident. Degrees, degrees, degrees. In terms of where it's going to land, right? I know that this at the y-axis from the initial side, I have 90 degrees, and half of that would be 45, so just under half, right? It's not, terribly picky, but you want to have a reasonable idea of where it's going to end. So this is 40 degrees. The coterminal angle with a 40-degree angle. Doing the same thing for B, we have 840 degrees. I have a feeling I'm going to go around 2 times. Let's try it. Yes. Just making sure you're not asleep at the wheel. Thank you. $720, same idea. I'm going to go around, so 720 minus 360, where does that put me? If it's less than 360, then I'll stop, but it is 360, which is kind of exciting. Which means I can go another rotation, and then that's it. So what does that look like? It means I'm going to go around 1 time, 2 times, and then I'm coterminal with 0 degrees. Yep. Now 840.
When writing that out, you have to go minus 360, minus 360, and you just know that it's going to end up.
You can just know that. Yeah. Because I mean, how do you know that? Well, you're chopping away 360 at a time, right? So you can just know that. It's okay. I just want to show where it's coming from. $840, doing the same thing. Take away 360. Puts me at 480, which is not within the 360, keeping track of how many times I subtract 360, of course. Minus 360. I get 120. Oh. So let's see here. I did 1 loop, and then I did another loop, and then I want to go 120 degrees, which is past the 90 degrees, but not getting to the, 180 degrees, right? And so somewhere in here, I'm not going to be too picky about it, but let's see. Let's take away 9, something like that. Looks good. Oops, wrong color. Pink. So it's coterminal with 120 degrees. negative angles just mean that you're moving clockwise instead of counterclockwise. Angle means move clockwise. I'll say instead of counterclockwise, which we usually do. So negative 60 degrees would look something like what? I want to go down from the initial side 60 degrees, right? Which is going to be within the 90 degrees. So somewhere kind of between the initial side and this negative y-axis. And so if I go here, let's put it somewhere like this. But we want an angle between 0 and 360 degrees, right? Which means that we want this angle, which will also be coterminal. So how are we going to find that? Well, there's a couple of different ways. We know the total rotation is 360, and then I've kind of backpedaled 60 of it, right? And so we could do it that way. So negative, let's say 360 minus 60 degrees. Just trying to do it fancy. All right, if this is 60, then this must be 300 degrees. Within those restrictions. Between 0 and 360. Nice. Well, negative 500. Do the same thing, but clockwise instead of counterclockwise. Can do that. Now, I want to do, I kind of, in my head, drop the negative and just remember which direction I'm moving. So 500 minus 360 is 140 degrees, which means moving in kind of the opposite way that I want. Moving this way now. That's 360, and then I want to move another 140 degrees. So that's going to be more than 90, but less than 180. Right? So somewhere in here. Oops. Now this distance, let's make it more clear. Must be 360 minus 140. Oops. Putting me at 220 degrees, which you can confirm, right, is past the 180 mark. Makes sense. So it's coterminal with 220 degrees. Questions about that? Then let's talk. Well, it kind of works. Talk arc length. Arc length is the length of an arc, of course. And we denote this arc by S. And so if we have a circle with radius R and it's subtended, which means kind of attached, I guess, by an angle theta, right? A generic angle theta, right? Then the arc length would be this length here on the outside of the circle, which means it's the portion of the circumference between the initial and the terminal sides of the angle, right? So it's the portion of the circumference, which is the outside of the circle, between the initial and the terminal sides. I'll put those on here. Initial and the terminal side. And it might be nice to remember the circumference of a circle is 2 pi r. If you know the radius, then the circumference is going to be 2 pi r, which kind of leads us into radians. I'm just going to sneak it in here because I think it is a little fun fact, an LFF, if you will. Little fun fact is that a radian measure is the length, the arc length, divided by r. And so it's going to be S over R, which means on the unit circle, right? So here, this means on the unit circle we introduced last day, right? It's centered at 0, 0 and has a radius of 1. And so it's a nice kind of basic circle to work with. And so this means on the unit circle where the radius is 1, right? Then if theta is 1 radian, right? A radian measure is S over R and the radius is 1, then S must be 1 in order to get to 1, right? And so it's if the radius is the same as the arc length, then the distance or this measure is 1 radian. So that's kind of cool. Bless you. 1 radian is 1 over 1. So S is 1 and R is 1. It would be true as long as S and R are the same, then you have made 1 radian. Radians are unitless versus degrees. Well, the degrees is the unit. Degrees have units. Degrees. So that's the benefit of working with radians. But like I said, we'll focus on degrees. That might be nice to know. Any questions about arc length, I guess? All right. If you have a circle of radius 6, so now I know my r is 6. Find the arc length, which is s, of a quarter rotation. And so we can draw a circle. And split it into quarters. I want a quarter rotation, which is this length here. Let's start. Oops, doesn't want it. I have to draw it properly. Come on. There. 1/4 rotation. So we want to find this radius is 6. And we want to find the arc length of this thing. Now, there's a couple of different ways that you could do it. But I think my way is going to be take the total circumference of a circle with radius 6 and then divide it into a quarter. And so I'm going to start with the circumference, which is 2 pi r. And then I'm going to let r be 6, which means the circumference, the total circumference, is 2 pi times 6. Pi is just a number, right? And so, and you've got a pi button on your calculator, which you can use, right? And so what we get is the circumference, the total circumference must be 12 pi, right? And if you want to, you can convert that to a decimal. I'm going to keep it as 12 pi. So now a quarter times the circumference, right? A quarter rotation is a quarter times 12 pi. Which puts me at 3 pi. That's this arc length. Oops. I wanted to elaborate on something, but I can't remember what. Anyways, we answered the questions. A person walks 140 degrees around a circle with a radius of 50 feet. How far do they walk? Which would be the arc length of the circle, right? And so let's map it out. We'll do, I'll make my grid first here. I'll put a circle on here. And I'm going to force the radius to be 50 feet. 140 degrees, knowing what we know about the circle, total 360. So it's somewhere past 90, but not hitting 180. Right, it'll be just past the halfway mark. But we'll show that by saying this is 140 degrees. We can solve it similar to how we solved this one, right? I could find the total circumference and then take the fraction that I want, right? In this case, the fraction's not a quarter anymore. The fraction that I would want is 140 out of 360 degrees, right? And so applying the same problem solving technique, let's find the total circumference. The circumference has to be the total, so we don't have to put the total, but I just want to emphasize that it's the full circumference as opposed to the arc length, right? We want to find this length here. Circumference is 2 pi r. And so the circumference is 2 pi times 50. So I get 100 pi. That's just a number, right? So it's just an exact number. Hey, 100 pi. The arc length will be 140 degrees, 140 360ths of C. And so I have 140 over 360, those units would cancel, right? Degrees over degrees times 100 pi. Let's see if I get anything nice. No, you don't. That's okay. Times 100 pi. My calculator tells me it's 350 over 9 times pi. That's how far do they walk? Well, that's hard to wrap your head around. Did you say 122? Nice. 122.173 feet. Exactly what you said, just slower. Nice. Of course, the exact answer would be fine. Nice. Questions about that one? Oh, then I guess we're on to the next section. Skipping radians kind of cuts out a lot. We didn't skip them, we're just not focusing. Everyone's favorite, SOHCAHTOA, focusing on the SOHCAH. Although Joy and I were talking, I guess she calls it SOHCAHTOA. I can't even say it. It's like, that's not how you say it. It makes it sound like S-A-H. Anyways, suck it to him. All right. Points on circles using sine and cosine. And so if we have a point on a circle like this, then what we could do is we could imagine a triangle in here. In fact, it would be a right triangle, right? Drop down on the x-axis and then figure out, I guess, drop onto the x-axis and then figure out what your y value is over here, okay, for your height. And so you get this right triangle. And if we have, for a point xy on a circle of radius r at an angle of theta, we can define two important functions as the ratios of the sides of the corresponding angle. So the sine function, sine theta, right? And I know you know. So ka, and we can squeeze in toa over there too, but we're not going to work with it. But in terms of what it would mean for the tan of theta, in terms of the circle, right? Here, you've got your opposite, you've got your adjacent, and you've got your hypotenuse. So your O is your Y, your A is your X, and your H is your R. Which means that the sine of theta would be the opposite over hypotenuse, which means it's y over r, in terms of if you have the radius. Now the cosine of theta, ka, is the adjacent over the hypotenuse, which means it's x over r. And then that means that the tan of theta, right, kind of a secondary player. Wait, don't do that. I was gonna move it over, but I guess I'll just squeeze it in. The tan of theta is the opposite over adjacent, which makes it y over x in terms of those coordinates. What's neat though is if you have an xy coordinate like this, and the sine of theta is y over r, for example, then what you could do is you could solve for y and say that y is r times the sine of theta, right? So if you have the radius and you have the theta, then it's going to be r sine theta. Right? That's cool. So here, on a circle of radius r at an angle of theta, we can find the coordinates of the point x and y at that angle using, well, we started here. Y is r times the sine of theta, right? Just multiplying this r over here. And x is going to be r times the cos of theta. Which means on a unit circle, right, which is a circle with radius 1 centered at 0, 0, x would be 1 times the cos of theta, and y would be 1 times the sine of theta. Right? And so then you can find your xy coordinates on the circle. In order to sort of slyly satisfy a learning outcome, I want to show you inverse functions. We don't have time to do them properly, but I'll show you what they are. So sine and cos are just functions, right? And so they have inverses. We have to restrict the domain, but they do have inverses, and your calculator has an inverse function button that we will use. So we're not going to go crazy, but let's see what I mean. On a circle of radius 5, there is a point 3, 4 at some angle theta. We want to find the cos of theta, the sine of theta, and I'm adding that we're going to solve for theta. Now, I'll start here and I'll draw a circle. It doesn't specify that it's off-centered or anything, so you can assume it's centered at the origin. But we do know that the radius is 5. And we have a point 3, 4, which means x is going to be 3 and y is going to be 4. I'm just going to guesstimate that it would be maybe somewhere here. And it is at some angle theta. And I know that r must still be 5, so I have the hypotenuse, right? But if I kind of zoom in here, what do I want to do? I want to map this down to make a right triangle, right? And so then I can find what my y is and what my x is. Of course, from this point, my distance on the x-axis has to be 3, and my distance on the y-axis has to be 4. So using our SOHCAHTOA first, but really just the SO and the CA, the cosine of theta is the adjacent over the hypotenuse, which is 3/5. And the sine of theta, since we've got our triangle mapped out, right, it's easy enough, is the opposite over the hypotenuse, which is 4/5. Now, to solve for theta, and I've got a picture of most of your calculators, right? Sine -1, cos -1, tan to the -1, those are the inverse functions, right? And so these are the inverse functions of your sine, cosine, and tangent. Now this is where you want to make sure that you're in degree mode, right? And it'll look like that. Yeah. You could give it in radians as long as you don't put degrees on it, right? That would be bad. And so to solve for theta in, for example, sine of theta equal to 4/5, then to shake out that theta, what do you need to do? You need to take the inverse sine, right? Take the inverse of 4/5. And so here, theta then is going to be the sine to the -1, which indicates the inverse of 4/5. So just move it to the other side. Use it as a function. So if you use your calculator, and use your inverse sine. It should show up as sine to the -1 of, and then we put in 4 divided by 5. I get a theta of roughly 53.13 degrees because I'm in degree mode. We can try it. I'll do it over here, or using the cosine of theta is equal to 3/5. Now, I'm expecting to get the same number, right? It should be the same angle. So I'm really hoping that we get the same number. Theta is going to be the cosine, the inverse cosine of 3/5. Inverse cosine of 3/5. What a relief. 53.13-ish degrees. So I'm just adding on that you should be able to solve for theta as well. Any questions about that? The Pythagorean identity, right? We've got the Pythagorean theorem, a squared plus b squared equals c squared, right? If we kind of take it a step further into a squared plus b squared equals c squared, right? And then your x is, well, let's derive it actually. Let's move this down here. The Pythagorean theorem is that a squared plus b squared is equal to c squared in a right triangle. And let me map it so that it matches here. I'll call this A, B, and C. Or we can replace it with x squared plus y squared is equal to r squared, right? This is your x, and this is your y, and this is your r. If you're working on a circle, right, with a coordinate system. But then we also said that x, right, is going to be r times the cosine of theta, right? And so recall that x is r cos theta. And y is r sine theta. Plugging those in, I get r cos theta squared plus r sine theta. I almost put the square on. Usually we put the square on the sine, but I'll do it on the outside. So substituting those general x's and y's in terms of sine and cosine. Now I'm multiplying inside here, right? And so what I can do is I can expand this, and this becomes r squared cos squared theta. Now I will make a note here that usually we write cos squared theta, but it's the same as cos theta squared. And so it just makes it a little bit nicer to look at as cosine squared theta, but it is just cos theta, then square it, right? Which is how you would have to do it on your calculator, because I'm pretty sure, no, it doesn't have a cosine squared button. That's okay. Right. And so this is just notation for the cosine, then square it. And then plus r squared sine squared theta, which is r squared. Now what I can do is I can pull out a common r squared here. R squared times cosine squared theta plus sine squared theta, which is r squared. And how neat. You can divide both sides by r squared and get the cosine squared theta plus the sine squared theta is r squared over r squared, which makes cosine squared theta plus sine squared theta is equal to 1. Notice that that's regardless of what the radius is. Right? Doesn't care what the radius is because it was divided out. For any radius. Once you divide it. So that's cool. That Pythagoras, he was onto something, huh? So for any angle theta, then the cosine squared theta plus the sine squared theta is going to be 1. And so this is what we call an identity. Right? And it's something that you're allowed to use, and you can use it to manipulate problems. Right? Such as this one. And I'm adding a second part of the problem, I guess. Find the sine of theta is what it should say. Sine of theta, but colloquially, sine. If the cosine of theta is 5 over 8. And then we're going to find theta. You could, of course, find theta right now, right? Because we already saw it. Could find theta right away. Since the cosine of theta is 5 over 8, then theta must be the inverse cosine of 5 over 8, which is what? Inverse cos of 5 over 8. I get a theta of 51.3178 degrees-ish. I don't want to use that to find my sine because you want to try to not rely on answers that you have found to find next answers, right? If you can. Sometimes you have to build on answers that you found. But if you can avoid it, then it's always a good idea to use only the information that's been provided, right? And so how are we going to do that? So now find sine of theta. We know that the cos of theta, and there's a couple of different ways that you could do it, right? You could build a triangle, right? And so then you would know that, okay, the cosine of theta has an adjacent of 5 and a hypotenuse of 8. And then you could solve for the opposite. So here I'll say you could use a triangle. Oops, doesn't look like triangle. But try the Pythagorean identity. So there's lots of different ways that you could solve it, right? I would like to try solving it with this identity. Right? How am I going to do that? Well, I have the cosine squared of theta plus the sine squared of theta is 1. Now I know the cosine of theta is 5/8, and recall, we can rewrite this as cosine theta all squared plus the sine of theta all squared is equal to 1. Those would be equivalent, right? Making it a little bit easier to see where you would substitute in your 5/8, which would be here. 5/8 squared plus the sine of theta squared is equal to 1. Hmm. 5 divided by 8, and then square that. I get a sine, oh, I shouldn't jump so far. I get 25/64 as the exact answer on my calculator. And when possible, try to use the exact answer. It gives me 0.390625 as a decimal. The sine of theta squared is equal to 1. So now if I do 1 minus, and this is just on your calculator, right? So you can work with the fractions. I know you can, but it's okay. You can just use your calculator. 1 minus that, I get sine theta squared is 39/64. I'm going to try to keep it on this page, but might be close. I know what I can do. Rewrite this as 5/8 squared. Just bought myself another line. If I want to solve for the sine of theta, take the square root of both sides. It's 36/64. Yeah, thank you. Just saw that on my calculator. Thank you. I get the sine of theta is the root of 39/8. Now, of course, if your calculator isn't giving you the exact answers, that's totally fine, right? You can use decimals. Right? Just try to avoid rounding until the very end. So the sine of theta, but because the cos of theta was given as an exact value, then ideally you would have the exact value. So I'll leave it at the exact value. It makes sense because SOHCAHTOA, TOA, both are over the hypotenuse, right? And so the hypotenuse should be 8. And if we do a quick sketch of the triangle, something like this, we have theta here, then the cosine of theta was going to be 5/8. Solving for this value here, oops, this doesn't look like 8. What would I get? I would get 8 squared minus 5 squared is 39. So I would get the root of 39. So you could use the triangle, or you could use the identity. I guess because I didn't show a lot of work for the triangle, it looks simpler, but I would say they're about the same amount of work, right? If you had to show how you got the root 39. So now, if I want to confirm that theta is roughly 5.3178 degrees, right? You could check again. Check theta. If the sine of theta is the root of 39 over 8, then theta must be the inverse sine of the root of 39 over 8. 39 divided by 8, inverse sine of that guy. Phew. 51.3178 degrees, which of course they should be the same. Nice. Any questions about that one? Nice. So lots of different ways that you can solve it. I want you to kind of think about how your brain wants to solve it and then do it that way. Leverage that. How about a word problem? Everyone's favorite thing. A boat is detected by a radar 8 miles away at 70 degrees north of east. Okay, and so north of east means from the horizontal axis, the positive horizontal axis, you want to go up. Okay, is how you read this. So north of east means from east, move up 70 degrees. To north. Huh? That's how you read those. All right. 8 miles away at 70 degrees north of east. So what I'll do is I'll put my never eat shredded wheat on here. And at some point, let's say here, I have 70 degrees and I have a boat. Let's put the boat here. It's a little sailboat. Whee! And the radius, it was 8 miles away. How many miles north and east of the radar is it? That's really just asking you to find, well, what's your X and what's your Y, right? And again, there's lots of different ways that you could solve it, right? You could use the fact that X is r cos theta. That might be nice. And Y is r sine theta. Huh? So we could use that, or you could sketch out the triangle. Right? I think I'll use those identities, right? That X is r cos theta and Y is r sine theta. They end up doing the same thing anyways. So I want to find, what color can I use here? Create, drop it down. I want to solve for X and I want to solve for Y. So how many miles north is your Y and east is your X of the radar? Actually, say that. X is, the radius is 8 and the cosine of 70 degrees, as long as you're in degree mode, right? You've got your cosine functions. We actually haven't used those yet, right? But I'm kind of assuming you're familiar, right? And so the cosine of 70, you should get 0.342 times 8. I get an X of roughly 2.736 miles. And Y is 8 times the sine of theta. Oops, sine of 70, sorry. Sine of 70 times 8. I get Y is roughly 7.5175 miles. I guess I should keep the same number of decimal places. We'll round to 8 here. You can confirm, right? Because now you have a value for the X. It is rounded, and so you have to be, there's a little bit of wiggle room, right? And so the cosine, right? Adjacent over hypotenuse, the cosine of 70, I have 2.736 divided by 8. And if I do the cosine of 70, I get a difference of 0. So they're the same. So how many miles north and east the boat is 7.518 miles north and 2.736 miles east of the radar. Okay. Bump this up. Must have drawn a bigger graph or something last time. Maybe I didn't put them side by side. How about a similar one with a twist? A canoe is 4 kilometers away from a lighthouse at 40 degrees south of west. Yeah? So that's going to determine what quadrant you're in, right? And so how many kilometers south and west is the canoe from the lighthouse? So we're going to sketch it out again. I guess not again. It's our first time seeing this problem. Let's get our ever eat shredded wheat on there. we've got our lighthouse, which I'll put at the center because that's kind of where it has to go. You know? At 40 degrees south of west. So that means that starting from the west, so the negative horizontal axis, you want to move south. And this distance here is going to be 40 degrees. So you want to be a little bit careful with what happens. And so now I've got my canoe. I guess it's kind of hard to draw a canoe. It's going to look a lot like my boat without a sail. Oh well. Here's my canoe, which means that it is 4 kilometers away. And how many kilometers south and west is the canoe from the lighthouse? And I'll extend this just a smidge, because I ended up drawing a oops. There. How many kilometers south, which is your x, and west, which is your boy. South, which is your y, and west, which is your x. Should have drawn those out first. Now, if you prefer, you can kind of ignore the negatives, right? And as long as you just see the triangle, right, with the 40 degrees here, and you've got your x here and your y here, right, then it's the same problem as what we had, right? It's just in a different quadrant. So let's see here. Yep. No, I don't want to introduce that. Okay, so what can we do when we live in a shoe? Well, I can see from here, right? You can use the identities that we used before. That's totally fine, right? Or if you just want to stick with SOHCAHTOA, totally fine, right? And so if we want to solve for x, for example, that's the adjacent. So then the cosine of 40 is going to be the adjacent over 4. Which of course would get you to this same spot, right? So now I have x is going to be 4 times the cosine of 40. Cosine, oops, not inverse cosine. Cosine of 40 times 4. I get x is 3.0642. Rounding a little bit. And same deal. If I want to solve for y now, right? Of course, this x is in the negative direction, right? And so if you were mapping it, you would want to say it's negative. But because we're talking about east and west, right, it would be 3.0642 kilometers west of the lighthouse, right? So we can drop the negative. And same idea. the sine of 40 degrees to get to your y, right? That's your opposite. And the hypotenuse, which means you have to use the sine, which is going to be y over 4. So y is going to be 4 times the sine of 40 degrees. 4 times sine of 40. I get 2.5712 kilometers, rounding again. So, how many kilometers south and west is the canoe from the lighthouse? Therefore, the canoe, oops, is 2.5712 kilometers south and 3.0642 kilometers west of the lighthouse. Nice. I don't have any more. That's it. Any questions though? No. So we'll do a trig review day on Tuesday and then final exam overview / a little bit of review on Thursday. And that's all she wrote. I hope you have a wonderful weekend. See you next week.